In this podcast, we're going to talk about the oxidation reactions that you would use in order to form both aldehydes and ketones.
All right, so when we talk about the formation of aldehydes and ketones, we have to talk about oxidation. So this is going to be hopefully familiar territory for you. And if you remember back to when we talked about oxidation reactions, we know that depending on what we start with for an alcohol is going to dictate what we produce. So a primary alcohol has a different product when oxidized than a secondary alcohol than a tertiary alcohol. So to get an aldehyde, you have to start with a primary alcohol. And remember, this can be further oxidized to produce a carboxylic acid. So if you start with a primary alcohol and you oxidize it, make sure that you show this reaction all the way through to carboxylic acid. All right, so here we have our primary alcohol, and this could be attached to 1 carbon, it could be attached to 20 carbons. It's just a random R group. What this doesn't show us are the carbon-hydrogen bonds that are on here. And those are important to remember that those are there because an oxidation is an increase in carbon-oxygen bonds and a decrease in carbon-hydrogen bonds. So our primary alcohol is going to lose 2 hydrogens and we're going to form a carbonyl. So the first product is an aldehyde. So we have our R group just the same as before. This was our alcohol carbon. We've created a carbonyl where we used to have our hydroxyl group, and we have still 1 carbon-hydrogen bond left. When we further oxidize that, we can further oxidize this because we still have a carbon-hydrogen bond. So when we further oxidize this, we lose that carbon-hydrogen bond and we replace it with a carbon-oxygen bond and we form a carboxylic acid. So let's go ahead and see this in practice. So again, I always like to start by naming it. That keeps me current on naming functional groups and families that I haven't seen in a while. So this is a 1, 2, 3, 4 carbon alcohol. So this is butanol. And because the hydroxyl group could either be in the 1 position or the 2 position, I do have to number this. So this is 1-butanol. And taking a quick look at the alcohol carbon, I see that it's attached to 2 hydrogen groups. So that tells me we have 1 R group and 2 hydrogen groups. That tells me that it's a primary alcohol, and it also tells me that once oxidized, it's going to first form an aldehyde. So in our first oxidation, our chain of hydrogens will not change. I'm going to remove 1 of these hydrogens, and I'm going to replace one of the carbon-hydrogen bonds with a carbon-oxygen bond. So I'm going to have a double bond between carbon and oxygen, forming a carbonyl. So this is my first stage. I now have an aldehyde, and because we like to practice, we are going to practice both IUPAC naming and common naming. For carbon aldehyde, IUPAC name is butanal. Make sure you emphasize the A so it doesn't sound like the alcohol ol. Okay, and we do not have to number this because aldehydes always have the carbonyl in the 1 position. If you were to name this using the common naming system, we use our new prefixes. 4 carbons is butyr, aldehyde. But wait, this undergoes further oxidation. We still have a carbon-hydrogen bond here. We can remove the carbon-hydrogen bond and we can replace it with an additional carbon-oxygen bond. So resulting, nothing changes with my carbon chain. We still have 4 carbons. I still have my carbonyl, but now I've added an additional carbon-oxygen bond in the form of an OH group. So we now have a carboxylic acid. We haven't learned how to name these yet. So for now, until we learn how to name carboxylic acids, it's okay just to say, I have formed a carboxylic acid. Never hurts to practice using a word equation because you could see either on an assessment. So we were told that 1-propanol is oxidized in the presence of potassium dichromate. All right, so 1-propanol is a 3-carbon alcohol. There's 2, 3. That looks like a primary alcohol to me, and it's oxidized in the presence of potassium dichromate. All right, So that's another oxidizing agent. Sometimes you'll be given a specific oxidizing agent, or you'll just put the O in brackets. In this case, I was told what the specific one was. We know that a primary alcohol will first turn to an aldehyde. So we form a carbonyl on the alcohol carbon. Okay, so we removed one of my carbon hydrogen bonds, and we replace it with a carbon oxygen bond, forming that carbonyl, or that double bond between carbon and oxygen. And for practice, this is a 3-carbon aldehyde. So this would be propanal. Still wouldn't have to number it. Or we would call this propion aldehyde. I'm going to use the word aldehyde that was already there. We are using our new prefixes for the common name of that. Either would be appropriate unless you're specifically asked for one or the other. Still have a carbon-hydrogen bond, so I can further oxidize this. We're going to remove this last hydrogen off of what was the alcohol carbon. So now we have a 3-carbon carboxylic acid. Just as a refresher, you guys have done this before, but oxidation of a secondary alcohol is how we form ketones. And as you know, ketones do not further oxidize because there's no longer any carbon-hydrogen bonds on that alcohol carbon to oxidize. So we start with our secondary alcohol, and it's secondary because your alcohol carbon is attached to 2 R groups and only 1 hydrogen. So in an oxidation reaction, we remove this carbon-hydrogen bond because we're decreasing carbon-hydrogen bonds, we're increasing carbon-oxygen bonds. We lose the hydrogen off the hydroxyl group, and we wind up with a new carbonyl. It is between 2 carbon chains, or 2 R groups, so it is technically a ketone. All right, let's practice with another example. So we were told that 2-propanol, so 2-propanol is a 3-carbon alcohol, and my OH group is on the 2nd carbon, so it's right in the center. Notice that I only have 1 hydrogen coming off of that carbon because that is the 4th bond for that carbon. So that tells me right away, since it's secondary, that it's only going to go through a single oxidation. We will remove this carbon-hydrogen bond, and we'll replace it with a 2nd carbon-oxygen bond. So again, we remove this hydrogen, and now we have a spot for a 2nd bond to form. And because it's good practice, let's name it. So this ketone is a 3-carbon ketone, so we could call this propanone. We would not have to number it technically, because to be a ketone, you have to be between 2 R groups, and this is the smallest ketone you can have. It is between a single carbon on each side, so it's assumed that it's in the middle position, or the only place it could be in the middle. If we were to name this using our common naming system, we would say that this is dimethyl ketone, or we would call this acetone. All right, so you may see this next reaction in lab. This is not one that you have to be responsible for on a test. It's just something that you might see in lab, and it is another example of an oxidation of an aldehyde. So Benedict's test is a test for aldehydes. Ketones will not react in the presence of Benedict's. That would give a negative test. So in the presence of an aldehyde, you are going to see a weak positive with Benedict's test. So starting with an aldehyde, Benedict's is kind of a clearish blue color. When you add Benedict's to an aldehyde, if it's a simple aldehyde, you're going to get a positive test, but it's not as clear as if you have an aldehyde with an adjacent OH group. So you have your carbonyl, and then right next door, the 2nd carbon is going to have an OH group. That's an adjacent OH group. It's called an alpha hydroxy aldehyde, because we would call this the alpha carbon. So if you have an aldehyde that has the hydroxyl group right next door, it's an alpha hydroxy aldehyde, you're going to get a very clear positive result. And so your Benedicts will react with that, and it's going to form a brick red precipitate, and that is crystal clear as being a positive test. So this test is good for distinguishing between aldehydes and ketones, and on a more subtle scale, it's also good for determining a simple aldehyde versus an aldehyde that has that alpha hydroxy group.